Good afternoon. We are engineers, experts in generating energy, expert in storing energy. So we are supposed to be full of energy. So possibly we need to do zot to have that energy. Students, please stand up. All the students, UCI students. We are going to do zot together. Are you ready? On 3, 1, 2, 3. Zot. Okay, thank you. Let's see if we have the energy. Good afternoon. Okay, that's good. Welcome to the Capstone showcase of the Master of Engineering program at the UCI Samuel School of Engineering. I would like to first thank all the company liaisons, all the sponsors that sponsored our Capstone projects for the last 3 years. I would like to thank them, and please join me to give a big round of applause. Thank you. Okay. First, we have the welcome by Professor Derek Dunn Ranking. Then we have the overview of the Capstone projects for the winter spring quarters. After that, we are going to have the project pitches, 7 minutes per project. And that is going to take 1 hour. After that, we have the poster and prototype and reception, which is going to be outside. Then at 4, we are going to come back here for the awards and celebration. And at the end, we are going to have the group photos. Okay, I would like to ask Professor Derek Dunn Ranking to please come and welcome all the guests.
Good afternoon. You don't have to say good afternoon. Good afternoon, everyone, and welcome to the showcase. As he said, I'm Derek Dunn Rankin. I'm the director of the Master of Engineering program. These welcomes would come from the dean, and he unfortunately couldn't make it today. He has another event. This is the week of events because graduation's happening. So he has another bunch of awards to give to the School of Engineering. But you all should know that he is so enthusiastic about the Master of Engineering program that he is telling everyone in the school that this is a model to follow for all the degrees coming through the school. So he is definitely interested in expanding this program in very big ways. And it is only because of the successes that you have already demonstrated in the performance in this program. So I want to thank all the students and the company liaisons for creating projects, problems that really drive engineering innovation, challenges, and learning in exactly the way that the Master of Engineering program was designed. So let me thank you all for that. I also want to thank you for being here because I know that the Capstone, based on all of our project experiences, is an exhausting experience that culminates today. You have had the good fortune of being driven a little bit earlier to create videos and posters of your work. So at least it isn't all done last night. Although I know that a lot of it is probably, in terms of the final performances, the last thing that broke, the last thing that got fixed happens at the last minute. So honestly, I am not surprised about where the energy has gone. I think you put it in exactly the right place. I also want to say, and this is a little bit of an aside about the zot notion. So I ask, how do you balance what is a professional demeanor with a zot encouragement. And the nice thing to me about this, and I've seen this happen through the whole of the administration in the School of Engineering, the deans, the chancellor, everyone is proud of their zot motion. And I take it as a sign of humility that is powerful, that you can still have a little bit of childish joy in the middle of what are extraordinary accomplishments, means that you are taking your skills seriously, but not so seriously that you don't listen to people that have come before you and have additional wisdom to share. And that's what the company liaisons provide, and that's what your advisors provide, and that's what your peers provide. So I think that you're all getting exactly the right kind of experience that we want, and I won't take any more time with my words. I would like to jump right in and hear all of you with your own voices describing the things that you've done. Thank you for being here, and thank you.
Thank you, Derek. Okay, so I'm not going to spend too much time up here, but I just wanted to frame up what we're going to see here. This represents a culmination of about 20 weeks plus of really hard work on the part of the groups. What you see before you are the delineation of the projects for this year. Today, we're celebrating 7 of these projects. Those are the ones shown on the left. Starting June 24th, I believe, we're going to have 3 additional projects that will culminate in December. So we'll look forward to reconvening at that point. The way this kind of works, we interact with different potential project sponsors, the different companies that are here today, and basically work up some ideas that they have an interest in working on. We have the cohort of students. They have interest in working on some of these projects. They have skills that they can bring to the table. And so we basically try to blend up a project team that hopefully is set up for success. You can see the colored circles at the left of each of the projects. Those represent the disciplines. One of the things we try to do here is have multidisciplinary projects. So blue is mechanical and aerospace, red is electrical and computer science, and green is BME. So without further ado, Team Advantech, do you want to come on up, and you guys will kick this thing off. Each team has 7 minutes. So this is going to be a bit of an elevator speech, if you will. You'll have time to talk to them more in the poster session.
Good afternoon. We are Team V Terminator, an IoT-based floral farm monitoring system sponsored by Advantech and UC Irvine. Let me introduce my team members. Hi, I'm Smriti Ganesh. I'm the team lead, and I was responsible for the MIO and Y subsystem. I was also responsible for the system integration.
Hello, everyone. I'm Gyanesh Shah, and I was part of the robot subsystem.
Hi, I'm Tanvir Hannan. I was the in charge of image processing subsystem.
Hello, my name is Charlotte Rumberget, and I was in charge of the pipe subsystem design.
Did you know that the US in 2022 alone spent over $500 million to meet its sunflower oil demands? With the growing demand of sunflower in the past couple of years, and with war tensions across national boundaries, this amount is only going to surge, which means that sunflower oil is going to become less accessible to common people in the US. We as a team wanted to create a solution that would bridge this gap, which basically meant that sunflower oil prices are going to be decoupled from factors such as war, labor, and demand. We came up with a solution that was predictive, proactive, and that was basically a weed monitoring system. Now you may wonder, why weed? Because poor weed management is one of the main reasons why oil content in sunflower seeds drastically reduced by 90%. So presenting to you Weed Terminator. The Weed Terminator basically predicts the emergence of weed, sprays herbicide proactively, sends user appropriate notifications, and also continuously monitors weed on the sunflower fields. So we have 4 subsystems involved: 1, MIO-wise, 2, image processing, 3, robo, and 4, the pump subsystem. Let's look at the MIO-wise subsystem. It consists of MIO 4012E and MIO 5272 and WISE 4012E. The MIO 5272 is a powerful single board computer that is run on Intel processor series. We have the WISE 4012E, which is an IoT wireless module that is used for input and output purposes in IoT development. Let us look at the weed emergence prediction. So we gather data of temperature and rain percentage for over 10 days from weather.com. And using that, we calculate a parameter called GDD, growing degree day. GDD that is accumulated over a period of days becomes cumulative GDD. Now the cumulative GDD that affects that affects weeds in sunflowers are as shown. Now using all this data, we come to a threshold date that includes the rain percentage so that the herbicide spray is not washed away by rain. So let's see what happens on the threshold date. So on the threshold date, the pump subsystem will be automatically run for about a minute. And upon successful completion of the pump run, we get appropriate user notifications to place the robo on the field.
Let us look at the robot subsystem. The robot subsystem consists of the Raspberry Pi, robot hat, Pi camera, and the ultrasonic sensor. This makes up the PiCar X robot. As you can see on the system diagram, the robot moves along the field along the path of the pipeline, and it captures the images of the base of the sunflower. Here, you can see the movement is done using Aruco marker detection and distance detection. The Pi camera captures the Aruco marker, and this is how it looks upon detection. Using the 7 markers and the ultrasonic sensor, we are able to navigate the robot on the field in a closed loop mechanism. The pictures captured by the robot of the base of the sunflowers are then uploaded to a Google Drive, which is then taken by the image processing for weed detection.
Let's dive into the image processing subsystem. For image processing, we gathered a comprehensive data set of over 4,500 images, and we used the model VGG19 for our testing and training. So at the beginning, we split the data set to training and validation data, and then we fed all the image through our model VGG19. The model VGG19 consists of 19 layers. Among those 19 layers, we have 16 convolution layer and 3 fully connected layer. Those convolution layer does the filtering job and get the features extraction. And also in between the convolution layer, we have 5 max pooling layer. Those max pooling layer reduces the dimensionality of the image by keeping the prominent features intact. And finally, the fully connected layer does the prediction, and at the end, the softmax activation layer does the classification job. We get images from the PiCar X robot every day, and by using our model, the prediction of weight in the field determined.
All right, so now let's move on to the pump subsystem. So as we can see here, the pump subsystem consists of 3 components. One is a vinyl pipe that carries the herbicide solution through the entire system. The second is what we have is a diaphragm pump that creates the pressure gradient in order to drive the herbicide system through the pipe. Finally, we have the nozzle here, which dispenses the herbicide solution and atomizes it such that it is dispensed at the roots of each plant. As we can see above, we have a little video of the nozzles working and the pump system being turned on. The 2 nozzles we see here are the ones shown in orange.
let's look at the cost analysis for our system. We compared with two existing weight control system available in the market. Those are manual weight control system and chemical weight control system, and they cost $144,000 US and $130,000 US for 3 years period of time for a 10-acre field. And with the implementation of our system with Terminator, the cost goes down significantly to $64,000. That demonstrate that our system is more than 2 times as cost effective than the other methods.
We spent 6 months on this journey, and let me show you some of the highlights. The first 2 months, we created the system diagram, tested the pumps and the robot. The next 2 months, we completed the image processing model and did a flow rate test of the pump. And the last 2 months, we finalized the GUI and did the overall system test. We would like to thank our Professor Farjad, and the company liaisons from Team Advantech. Thank you.
Thank you.
Hello, welcome to our showcase presentation. This year, we worked with Depress System on a brain band, which is a non-invasive technology to improve mood and memory. The team consisted of myself, Athena, I was the team lead. We had Sylvia as our test engineer, Sydney as our design and biomedical engineer, and Matthew as our mechanical engineer.
So depression is a mental health condition that can have a deep impact on a person's thoughts, emotions, and overall well-being. There are a variety of factors that can contribute to depression. And according to the World Health Organization, 280 million people suffer from depression worldwide. So the main goal of our project is to develop a brain band that can effectively transmit electrical stimulation to the brain and help reduce the symptoms that are associated with depression. This means upregulating proteins of klotho, BDNF, and serotonin. So the top 5 needs that we wanted to meet for our project was making sure we had electrical stimulation, protein upregulation, a comfortable and portable device, and making even skin contact with the device. And so based on the metrics from the company prototype and the ideal values, our final prototype was able to improve in 4 out of the 5 categories. So as part of our project breakdown, we first have the sponge and saline. This is meant to evenly distribute the current to the brain. Next, we have the electrode, which houses these components and delivers the current to the brain. The brain band that houses everything together makes it comfortable and stable to use. And the HTM stim unit, which is what actually creates the current that's being delivered to the brain. So as part of our testing, we had the sponge. We tested 3 different types of materials and thicknesses. First, we have the Gainwell sponge, which is a cellulose-based sponge, a lifted sponge, which is our competitor sponge, and then the makeup sponge, which is a polyurethane-based sponge. So based off of the testing, the different materials and absorbencies, we detected that the Gainwell sponge was the best option. So then after selecting the sponge, we went in and did saline conductivity testing. We tested 4 different concentrations. And based off of the results, we found that the 80 millimolar saline solution had the most consistency values and the highest conductivity.
Since the brain band will be worn on the head, we did extensive research so that it doesn't harm the user. As you can see, there are many different electrode material types ranging from metal EEG ones to entire cap configurations, but in the long run, we ended up choosing the conductive rubber material as one, it is very conductive, and second, since it is non-metal, it doesn't participate in electrochemical reactions, and with these properties along with its roundness and shape, these both provide an electrical distribution that won't damage the user's skin and burn it. Regarding the size, we chose a 25 centimeter squared surface area as it distributes the current evenly, and it provides the best density to reach the thalamus part of the brain and improve depression.
With the electrodes, we also had to consider a factor known as shunting. So shunting is basically when treatment happens across the brain as opposed to deep brain tissue. And so on the side, we actually have two photos. So we have no shunting on the left and shunting on the right to kind of compare and contrast how these would look. And so in order to avoid shunting, because we would want the deep brain tissue to receive the treatment, we would need to consider how big our sponge is. So since we would use a 25 centimeters squared sponge and electrode treatment, we would need these to be 5 centimeters distance apart, measured from one center of the electrode to the other center of the electrode. However, in our testing, we were able to push this to 6 to 7 centimeters apart. In regards to their placements, we decided to use a two-system electrode. So we have an F3 and an F4 system. And this is because when we place the electrodes on these 2 points, these are associated with regulating the thoughts and emotions and the actions of the brain. In comparison, we also had a rat model to do for a wet lab study. Because there was no previous studies out there on where the electrode placement should be, we actually had to model these on the Soterix medical software. And so we had the B, C, and D placements. From these comparisons, we can see that the B1 and B2 were actually ideal. And this is because the actual electrical treatment is spread across the brain. It's also even, thus avoiding hot spots for our user. And then when we actually were able to take these into slices, we had a coronal, sagittal, and axial slice. So the top portion is the human brain and the bottom version is the rat brain. From these, we can see the field intensity, which red being the highest as it continues to disperse across and travel through the brain in the vortex waves that we see here. And if I will zoom in on the coronal slice of the brain itself, there is something known as the vortex and thalamus, and this actually monitors the production of serotonin and BDNF. From the spherical models, when we zoom in, we can see that it's actually receiving treatment all the way through, and the field intensity doesn't hit 0 until the back of the brain.
Here we can see a summary of the physical prototypes that we worked on during the course of this project. Starting in the top left and working our way clockwise, we have the initial prototype that was provided to us by the company. We spent the first 10 weeks iterating on that prototype. And then in the beginning of the second quarter, we developed our own prototype that was focused on being a lot smaller and lighter. This one had a handful of iterations, mostly due to some space constraints, which resulted in our final prototype on the bottom left. Here we can see a more in-depth view of the CAD model for our final prototype, including an exploded view of it on the right-hand side.
So this is our entire complete prototype setup on the left, and to see how it's connected internally, you can see that on the right. To see how all this works, what we could do is turn on the stimulation unit to a 2 milliamp direct current output. This should send it to the electrode, in which we can use a multimeter to complete the circuit. Here we can get an output reading, and if that reading matches for the electrodes to the stim unit, it indicates that the whole system does work. And from our testing, our prototype does work.
As part of our development process, we ran a thermal analysis to determine if the electrodes would heat up to the point of burning the skin of the user upon use. For this, we assumed that all of the electricity going through the electrode would be converted into heat instead of being transmitted into the brain. This gave us a heat power of 27 milliwatts, which includes a factor of safety of 3. For convection coefficients, we used 1 watt per meter Kelvin on external facing surfaces and 0.1 for internal facing surfaces. Upon running the simulation, we had a maximum temperature of about 36.7 degrees Celsius, which is less than the FDA regulated temperatures of 42 degrees Celsius, and even less than the average human temperature of 37 degrees. In fact, during our simulations, we even observed that more heat was being transferred from the skin of the user to the electrode than vice versa.
And that concludes our presentation. So we would like to thank the Leonhardts for being our sponsors, as well as Professor Harsab. Thank you.
All right, thanks for everybody joining us today. We're Team Massimo, and for our project, we worked on a predictive simulation model for a high accuracy temperature probe. So essentially, we worked on a continuous thermometer. So I'd like to introduce myself. My name's Jack, Rashid, Bobby, Emily, Akira, and Nong. We all respectively worked on different aspects of the project and brought them all together to finish it. About our project. On the right-hand side of the screen, you'll see Massimo's Radius T sensor. This sensor already exists, and Massimo would like to iterate on it and make it even better. So they provided this project to us to make its accuracy even better than it already is, and gave us a plus or minus 1.5% variance requirement. So to approach this process, we first, on our timeline, characterized the materials in the stack. We then applied it to the three-dimensional model provided by Massimo. We then collected test data and validated the model. And then today we're here to share that final model with you today. So a bit about the project's relevance and why it's important. This simulation is going to help a group of algorithm engineers at Massimo build out the core body temperature model that they're working on. They're algorithm engineers and they don't always understand mechanical engineering or the physical properties of these materials. So by providing them a simulation, they can make their core body temperature algorithm that much better. The intended output relevance as a whole is to make continuous monitoring of rapid body changes temperature that much better for hospitals and home use. So a bit about the abstract. What you're looking at here is a two-dimensional cross-section of the sensor. You can see that there's 4 temperature integrated circuits, T1 through T4, that are what the algorithm engineers are looking at to build out their core body temperature. Our job was to essentially build the most accurate roadmap of this temperature stack and provide this to them. At the bottom, you can see the heat source being the skin that the sensor is placed on.
So getting into the data collection test setup, on the left-hand side, you can see the environmental chamber that we use to isolate what we're analyzing versus the environment. On the middle half of the screen, you can see that we had temperature sensors installed within to monitor the temperature of each IC as we go through that heating process. And lastly, you can see our ambient temperature chosen as 25 degrees Celsius to monitor the ISO standards and internationally regulated inpatient settings, and a Peltier heater, which was using a skin temperature of 35 degrees Celsius.
Another area that we were interested to see if there is any heat generated from the ICs on the board inside the module. We studied the circuit and basically calculate current and power that goes through all the chipsets inside the circuit. And upon calculating all this and summing up, we realized that the amount of energy that is generated inside the module is negligible. So it's not really affecting our calculations.
So we were given the SolidWorks model of the part. So that's a 3D model, and it came with a lot of really small details for all of the parts in the assembly. So in order to get it into the COMSOL simulation software, we had to simplify the model and remove all of those small details. And in some cases, we had to remake some of the parts so that they could work. For example, that outer case on the top has a lot of ridges and curves, and I remodeled that as a simple rectangle. This allowed us to add the physics to the COMSOL model. And then from there, we had to also add the airflow or convection to the COMSOL model. And in order to do this, we had to model the air itself as a 3D component and put that into the model. When doing this, we got a lot of issues with the interference and parts just slightly overlapping with each other. And that was a really lengthy process to solve, but it proved to be essential for making our COMSOL model work.
So the goal of our COMSOL model was to accurately replicate the steady state and time dependent behavior of our RTR physical model. What we did was conduct a heat transfer and fluid dynamics multi-physics coupling analysis in COMSOL to analyze how our numerical model behaves towards changes in the boundary conditions. Some of the boundary conditions that we explored were the heat transfer convection coefficient into the ambient air, as well as the temperature of the skin that we modeled as a constant heat source. On the slide here, we see the time-dependent analysis for 2 of our models. On the left is our initial simplified 2D cross-section of the RTR device, and on the right is the cross-section of the 3D model. The four numbers you see represent the four temperature ICs that are present on the physical RTR that we modeled as a temperature probe in the numerical model. And from these four temperature probes, we're able to get the temperature data that we compared with the experimental data.
After get the model in the console, we run several sensitivity studies to indicate the performance of our console model. And you can see on the screen, we focus on four main features here. First is the geometry, convection coefficient, airflow, and PCB structure. It comes with a different parameter. We run to the data analysis. And our data analysis run with the flowchart on the screen. And first, after we get the drawing data from console and physical model, we clean and visualize it into the live wrap to see how the fitness of console model with a different parameter. You can see on the screen here, this is our the wrap for visualization data on IC number 2. We have the error bar. The solid line indicate that the real system or the actual data, and the last line represents for parameter conversion come from the console generated it. It's clearly to see that the conversion coefficient equal 10 give us the high accuracy. However, we still need some numerical data to prove that visual result is correct or not. That's why we calculate the root mean square error. And finally, after calculate sum up and get some number, we come with the best package of the parameter for our model.
So the final project result ended up in that 1.5% accuracy variation that we talked about at the very beginning. So as you can see, temperature ICs 1 and 3 had a variation of about 1.4%, and temperature ICs 2 and 4 had about 0.5% variation. So our final project deliverables were successful, and we're ultimately delivering a project that was a huge success. We want to say a big thank you to the faculty advisors and company liaisons for the support throughout this project. Thank you.
Hello, everybody. My name is Spencer Joseph, and I led the Capstone project sponsored by Major Genetics to develop a prototype for an advanced wound care device. In austere battlefield situations, severe burns can be much more dangerous to burn soldiers. Combat medics don't have access to equipment that offers infection prevention and is an alternative to postponed surgery. Skin grafting is how we heal burns, but there are some drawbacks. First, it is not available in the field setting, requiring a clinic to perform. Second, it is an expensive and time-consuming operation. And lastly, it is a notoriously painful process and can leave scarring and discoloration of the body. If only there were a way for burns to be healed on the field. We present the Spin Heal as the portable solution for burn treatment. The Spin Heal is a handheld applicator capable of spraying a wound with a nanofiber healing matrix. The dressing is applied with minimal contact from the medic. The dressing can have functional additives such as antibiotics and painkillers to best suit the victim's needs. The device is portable and handheld, relying on battery power and cartridges alone. The device is lightweight, designed to be carried in a burn bag. The dressing is transparent, so the doctor is able to monitor the healing process without interrupting it. The device uses patented force spinning technology to produce nanofibers.
In the military, severe burns make up to 8% of all combat injuries. They are actively trying to improve the treatment of burn soldiers as they take 4 days to reach a nearest burn center. Not only that, 40,000 citizens in the US are hospitalized annually from second and third degree burns. And in terms of marketing, the global burn care market was valued at $2.43 billion in 2022. And as you can see from the graph, it is projected to expand at 7.1% annually. There is also a major potential to improve the healing process and outcome, as well as reducing the resource spent on burn victims. Here, we would like to propose our alternative solution for wound treatment, nanofiber dressings. Nanofiber dressings spun from polymer solution have been proven to regenerate tissues, with their structure mimicking human skin layers, allowing cells to move into their porous structure and form new healthy granulation tissues, leading to tissue regeneration. Additionally, incorporation of antibiotics or antimicrobial substance can help to prevent or treat infection at wounded sites.
In developing our handheld device, we began with our lab model. So this allowed us to focus on the production of nanofiber before we designed the handheld device. So we already know how nanofibers can be used in wound treatment. So the next step is how we're going to apply that. We're using a pattern technology called the force spinning. So what is force spinning? Basically, it is a method of producing nanofiber using centrifugal force to draw polymer solutions through a spinneret to form fibers in nanoscale. When the spinneret is spinning, the solutions inside the spinneret will be stretched due to the centrifugal force. And if the centrifugal force can exceed the surface tension between liquid molecules, you'll stretch out the liquid to form fiber jets. And if the fiber jet diameter is in the nanoscale, then it's called nanofiber. So based on that, we built our lab model to verify our ideas and assumptions using the following equation of centrifugal force and surface tension to calculate the rotating speed we need. After that, we improve our spinneret design and make the device portable and battery operated. So let me show you how this device works. On the right-hand side, you can see when we pull the trigger, the motor starts to spin. Then the power will be transferred using the bevel gear pair onto the main shaft. The fan and the spinneret containing our solutions are attached to the shaft. So when the shaft is spinning, the fan can create a steady airflow toward the front. So when fibers are ejected out from the spinneret, they can enter the flow and then guide toward the nozzle of the device. Then the fibers can be deposited onto the target area.
Next, I'm going to demonstrate our device. So to spread a fiber, simply turn the switch on and pull the trigger. The fiber will come out from the device and cover the target area. As you can see now, the fiber is coming out from our spinneret. With the advantage of covering any size of wound, our final product can be a substitute for the current wound dressing. After applying nanofiber mat on the wound, doctor can still observe the wound by spraying water on it to make it transparent.
In summary, we have developed a proof of concept prototype for SpinHeal, a point of care device for wound healing. This targets military applications, addressing accessibility concerns and reducing the risk associated with delayed surgery. We have improved the mechanical design for increased nanofiber production. This has been a valuable learning experience through iterative development. On behalf of the team, I'd like to thank the liaisons from Major Genetics, Dr. Shreve Solomon and Dr. Samir Shrine, the UCI MENG program, and our advisor, Dr. Vince McDonald. Please use this QR code to learn more about our project, and we'd love to talk to you more and show off the device at the poster session.
We are Team Mitsubishi Electric, and our product is improved warehouse efficiency and flexibility through drone-based autonomous warehouse logistics, or in short, we're emulating a drone in a warehouse setting, picking up and transporting packages. My name is Eric. I'm the team lead, and I've been responsible for project management, hardware setup, and pose estimation.
My name is T-Yun. I'm responsible for designing the gripper and programming the camera.
And my name is Zhang Huang. I'm responsible for the design of gripper carriage and the movement mechanism.
My name is Li Hongbai. In this project, I trained the object detection models and wrote the box selection algorithms.
So our idea came out of a Mitsubishi project that would want to deliver small volumes of items by drone to the place which can be difficult for a human to reach. The drone delivery can not only improve the efficiency of delivery, but also greatly reduce the cost of labor. In addition, the small size of drone can easily adapt to complex environments, such as shelves and a warehouse. So at this stage, our task is to set up a movement mechanism on a set of 3D printer, which can identify and locate the package with the help of computer vision.
Here you can see our system, and it comprises of a 3D printer. So we have 4 degrees of freedom, the 3 translations from the printer. We've also added a rotational degree of freedom in addition to the gripping actuator. We've attached a depth camera to get depth information on the boxes to be able to locate them. Using this, we process the data into an area center with an angle. That way we can fully define where the boxes are. And we can move the gripper to the area center, rotate about the specified angle, and grab each box.
The main part of our software is executed on the JSON Nano, which is our processing unit. The Nano is connected to the camera, which is our the JSON Nano is connected to the camera to retrieve the images, and to the Octopus, which is our microcontroller for the movement mechanisms. The Octopus transforms the generated G-code into the step commands, as you can see in the bottom left, for the movement mechanisms. This then motivates the gripper to move and allowing us to grab the packages. This is what our 3D printed gripper and carriage assembly look like. Overall, most part fits very well and have high 3D printing quality. Figure on the right-hand side is an exploded view of our final chuck-based gripper design.
Our main program starts with checking the home position of the printer and getting the sensors data, such as the RGB image and the depth image. Sending these two into the segmentation models and the box selections algorithms, we are able to get information like the dimensions, coordinates, and the rotation angles of the boxes. With these geometries, we are able to give G-codes and we're able to give the G-codes to the gripper and move the boxes. Each time after the gripper moves the box, the printer will go back to the home position, and until all the boxes are relocated or no boxes are detected in the site. If we take a closer look on the object segmentation models, it is trained on YOLO version 8 and based on the dataset OSCD, stands for the stack cartons. And the other 20% are the pictures we took ourselves, where we apply augmentations like rotations and shearing. And up to this point, we get an average precision of 87% for medium-sized objects.
Next is pose estimation. We've chosen a fairly simple approach here to fit a rectangle to the 2D image plane. We use the object segmentation mask to do this. And by fitting the rectangle, we get the area center, width, height, and angle of each box in the image plane. This is then converted to camera coordinates using the depth information from the depth camera. And then, as mentioned, we simply move the gripper to the area center and grab the box that was selected. Here you can see our prototype in action. After all the data is processed and the box is selected, we move over to and grab the box. And to emulate the drone, we are moving it to a destination. In this case, to keep it simple, we are doing a drop in each corner before it returns to the home position, ready to pick the next box.
We can upgrade our prototypes in many ways. For example, we can apply 3D estimations, 3D pose estimations to get the rotations about all 3 axes. We can add a load cell on the grippers to make it a closed loop. We can use world's coordinates instead of on the camera, or we can improve our computer vision algorithms by increasing the size and the quality of the data sets.
Thank you so much for listening to our presentation. We would like to thank you, Mitsubishi Electric and UCI for providing us opportunities to work on this project.
Hello, everyone, and thank you for joining us today. Our capstone project was with MIVI Neuroscience, and we worked on the implementation of real-time pulsatile aspiration control for ischemic stroke treatment. This is our team. We have myself, Aaron Flores, along with Ali, Jose, and Arjun.
Nearly 800,000 people are diagnosed with stroke annually. Stroke occurs when blood is prevented to go to the brain. Mechanical thrombectomy is a procedure to treat ischemic stroke, emphasizes in swift removal of blood clots from blocked arteries. Therefore, it restores the blood flow to the brain and it minimizes the potential damage. So our project is to improve clot aspiration to decrease procedural time.
Shown here is a mechanical thrombectomy procedure. Once the location of the clot is identified, the surgeon will place the catheter into the femoral artery and guide it to the location of the clot. Once the catheter is adjacent to the clot, the aspiration begins. After the removal of the clot, the catheter is removed and blood flow will be restored to the region of the brain that was blocked by the clot.
Theoretically, there are many ways to improve aspiration time. That includes increasing the radius of the catheter, decreasing the viscosity of the fluid, reducing the length of the catheter, increasing the pressure gradient, or using a pulsating suction technique. Our project focuses on implementing the pulsating suction technique, as most catheters available on the market today use the constant aspiration technique. With that, our project objective is to develop a real-time pulsatile aspiration method to decrease clot aspiration time. Our goal is to improve patient outcomes during thrombectomy procedures.
MiViQ catheter consists of short flexible section attached to a 0.02-inch push wire and an innovative guide catheter lumen that maximizes the average diameter of the system. MiViQ catheter consists of 4 different catheters: Q3, Q4, Q5, and Q6. The diagram below illustrates the comparison of MiViQ catheter to the other standard catheters. MiViQ catheter has a larger proximal ID. This innovative design allows for much faster aspiration rate compared to other catheters. As shown in this example video, Q6 catheter has faster aspiration rate compared to other catheters in the market right now.
This chart represents the number of trials we have conducted. During the first half, we did some pulsatile methods doing various combinations of solenoid on and off duration. This helped us to identify and develop live algorithm trials such as single threshold, dual threshold, multi-pulse, stat pulse, and compare them to constant trials. And in total, we have completed about 243 trials.
So one of the key components to achieve our objective of reducing clot aspiration time is our custom trial procedure. Now, our procedure consists of 2 phases, the calibration phase and the clot aspiration phase. The calibration phase calculates the max flow rate and pressure regardless of the catheter system configuration. The clot aspiration phase is what our algorithm actually acts upon. We define specific thresholds during the calibration phase, and if the flow rate drops below those thresholds, we'll actually actuate a solenoid valve. This is to reduce, the key purpose of this is to reduce the system ingestion time, which we define as the time it takes for the clot to be ingested into the collection canister. So let's take a look at this in more detail. So here we have one of our algorithms, the stat pulse algorithm, that takes into account 12 data points and compares it with a specified flow rate threshold. If it's below that threshold, then the solenoid valve will close, which causes an increase in pressure and a decrease in flow rate to the minimum value. Once we open the solenoid valve again, we have a large pressure differential. And so in result, if we have a large pressure differential, it should theoretically improve volumetric flow rate. And so as a result, increase in volumetric flow rate reduces clot aspiration time.
The box plots shown here represent trials performed on live pulsatile algorithm from June 2nd and June 6th on soft clots measuring 2 ± 2 millimeters in length. On the left, we have a graph of trials performed on the Q4 catheter, where we found that on average, the multi-pulse method had a consistently faster system ingestion time. However, due to the large spread in data, we believe that additional trials are necessary in order to prove the efficacy of this result. On the right, we have a graph of trials performed on the Q5 catheter, where we compared algorithm methods called stat pulse, dual threshold, and single threshold against constant trials. We found that on average, the stat pulse method had the consistently shortest system ingestion time compared to constant trials. We believe that the two identified methods, multi-pulse and stat pulse, should continue to be explored in future. Our findings represent significant advancements in the field of ischemic stroke treatment. First, we optimize the solenoid on and off durations in order to ensure efficient pulse delivery. And we use that along with the identified control logic patterns for our pulsatile algorithm development. We then refined the algorithm through extensive testing of the 4 method types and evaluated their performance against constant trials. We were able to meet all of the project requirements. And these findings provided valuable insights towards future development and continue to contribute towards enhancing ischemic stroke treatment and improving patient outcomes. We'd like to thank MIVI Neuroscience for sponsoring this project along with our company liaisons and our fellow colleagues, as well as our faculty advisor, Vince McDonald. Thank you everyone for joining.
Good afternoon, everyone. My name is Juliana Tampis, and I am here with Innovative Cooling Solutions, brought to you by True Zero.
My name is Ziad.
I'm Boyan.
My name is Da.
And together we'd like to thank our faculty advisor, Vince McDonald, as well as our company liaisons, Tim Brown and Greg Wallace. Hydrogen-fueled vehicles have been on the rise within recent years. An example of one here is the Toyota Mirai, which maybe you've seen around. True Zero is an industry leader in owning and operating hydrogen fueling stations. They own and operate 41 stations in California alone. The station that we decided to focus on was in Costa Mesa. At this station, liquid hydrogen is delivered in a large semi-truck, similar to how a gas station operates. This liquid hydrogen is then vaporized and compressed to a very high pressure for storage. Once a vehicle is ready to be fueled up, this storage hydrogen is then gone through a series of heat exchanges to cool it down. This hydrogen is then entering the vehicle at -40°C with a pressure of 700 bar.
Okay, so I'm going to talk about the fuel stations. So True Zero has hydrogen fuel stations that store cooled brine. Now, the brine goes through a series of heat exchangers to cool down the hydrogen. And then once the hydrogen gets to a certain temperature, it is dispensed into the car. What we're trying to characterize here is the heat transfer of the heat exchanger, the heat transfer of the boil-off line, and the heat transfer of the dispenser, which is outside where the cars are being fueled.
A big part of the whole project was characterizing the different kinds of heat transfer, so which can be summed up in 3 different processes. The first one is the boil-off heat transfer. So hydrogen is stored in a large container where, due to its characteristics, some of it eventually boils off. So True Zero managed to use that hydrogen to cool the brine, to partially cool the brine, which is then later used. To characterize the boil-off heat transfer, we measured the temperature of the boil-off at 2 separate points, right after exiting the hydrogen tank and after exiting the brine tank. The temperature difference between these 2 points was around 132 degrees, or the heat transfer rate of just below 2,800 watts per second. The second point was the heat transfer rate. So as previously mentioned, the station consists of a series of heat exchangers through which hydrogen and brine are pumped. The point of this part of the process is to further cool the brine, which is later used and we'll mention how. So at this part of the process, the heat transfer rate is just below 3,800 watts per second. Our third and last point of research in the heat transfer rate was the pump heat exchanger. So this is the last part of the process right before fuel is dispensed into a car. So in order for the fuel to be dispensed into a vehicle, it needs to have a temperature of around -40°C. And to get this temperature for the now ambient temperature hydrogen, we need to use the now cold brine. So for the pump heat exchanger, the heat transfer efficiency is around 4,800 watts per second. So all in all, for all heat transfers, we can say that they're pretty efficient.
To make sure the brine's quality is good, we run two phases of brine analysis. In phase one, we tested the pH value and the specific density of the brine solution. As you can see on the screen, the brine samples we have collected from the fueling station is murky and discolored. In the second phase of the test, we tested the ion concentration and freezing points of the brine solutions. We used inductively coupled plasma mass spectrometer to analyze the ion content, the ion contamination level of the brine samples. You can see the result on the screen.
Additionally, we wanted to really characterize the energy loss from uninsulated pipes. These pipes may be uninsulated because insulation corrosion or they're large valves. As you can see on this screen, it just occurred, the overnight melt that happens, well, the daily melt, since it's very cold, there's ice buildup in the uninsulated regions. This actually melts completely away each night and then is built back up every single day. So this is considered energy loss from uninsulation. And in order to characterize this, we averaged 4 nights of ice melt. We used the latent heat of fusion and basically calculated the mass melt per square inch per night. And using the total uninsulated surface area of these pipes, we found the average nightly energy loss to be 2,700 kilojoules, which is a pretty low number, which means the insulation is not really impacting the station too much.
So the three main takeaways of this project, number one, the heat transfer rate. The heat transfer rates were very high. The higher the thermal conductivity of a fluid, the higher the heat transfer coefficient, which ultimately means the more efficient the system is. As my colleague Don mentioned, there were contaminants found in the brine samples that we collected. Those contaminants were formed due to the high pressure of the fluid running through the pipes, which over time causes gradual erosion within the pipes. We also tested for the freezing point of the brine. And we also noticed that the freezing point was significantly higher than what the company manufacturer has said on the data sheet. Last but not least, the energy loss from uninsulated pipes. We realized that the energy loss is so insignificant or too low that it doesn't affect the cooling system much, the overall general cooling system.
Thank you again to our faculty advisors and company liaisons. We couldn't have done it without you. And we hope you stop by our station outside to see Daw do a live demo of one of our brines actually doing a freezing point test in a cryo cooler that he manufactured himself. Very interesting. Anyways, thank you.
Thank you, everyone.
Great. Okay, what do you guys think? A lot of pretty cool stuff. So it was very exciting working with the teams during these past 2 quarters. At this point, we'd like to open it up for questions, but we're going to do that in the comfort of the reception hall at the posters. There's demonstrations there. There's some refreshments that you can enjoy. So So I'd like to have us adjourn at this point. You'll go out and to the left to get to the posters and the refreshments. Very important, please come back here at 4 o'clock. We'll make that announcement over in the poster room to come back here for a presentation of awards and again, to help us continue to celebrate the students and their great projects. So thank you very much, and we'll see you in the reception.
Okay. Time for awards. Seven amazing projects and 7 great sponsors. Wonderful support from the company liaisons. It means it's very difficult to pick the winners. Okay, so before we go with the awards, let's all thank the company liaisons for each project. And we are going to ask the team and the company liaisons for each project to come forward, starting from Advantech. So Advantech team and company liaison, Mr. Kevin, please come forward. I would like to also thank Mr. Joe Sangha, Mr. Joseph Su, and all the other company liaisons in Advantech. They had a huge meeting, or actually they have a huge meeting in Advantech, and they could not make that. Thank you very much, Mr. Kevin, for joining us. Thank you. Thank you for all. Kevin, if you would like to provide some comments, and the team lead, if you would like to have your comments about the project.
Yeah, I think it's great because I participated this project around maybe 4 months.
4 months.
Yeah, 4 months. At the beginning, I think they learn a lot. At the beginning, they don't know how to group up each other. Finally, they are team and made a great project. I think that's great.
Thank you. Thank you very much. Smriti?
Good evening, everyone. It was a great journey. It was really amazing because we got to understand that an engineer is always constrained by 3 factors: scope, time, and the amount of money that you get to spend. And it did show up a lot in the project. We were constrained by one of these factors at some point eventually in our project. And we also got to understand the discipline and focus it requires to meet deadlines and to be responsible towards your commitments. It's been a wonderful journey. The Advantech company liaisons were awesome. They came in with consistent feedback every week. And Professor Farzad was there helping us through every step whenever we had a doubt. So a huge thank you to UCI for organizing this, to the Advantech company for believing in our vision, and to Professor Farzad for always supporting us. Thank you. Thank you so much.
Thank you. Thank you very much, Team Atlantic. Thank you. Thank you. Appreciate your great support. Thank you. Thank you very much. Team Depress System, please come forward. So we are going to start with the company liaisons and then the team lead.
Okay, I would like to thank in my name and the name of Mr. Howard Leonhardt and Mrs. Kelsey Leonhardt the opportunity to support this group in this very amazing project. In my personal name, as an old professor, I have 43 years teaching. I started 43 years ago in South America, and I have been teaching in other countries in South America, Europe, and here at Pittsburgh and Utah University. I don't want to let pass this opportunity to congratulate the institution for the brilliant students that you have. I am really impressed with the quality of this team and of course with the others that I have the opportunity to hear today. At all then, thank you very much.
Thank you very much. Thank you for all the support. Appreciate it. Thank you. Thank you so much. Thank you.
I think it was just a really great experience for my team and I to continue to work with this company. It was great exposure to industry for ourselves. And just on top of that, I think we came in, none of us were actually experienced in electronics. So it was a good time to get exposed to bioelectronics and build that onto just our background and knowledge. So thank you.
Thank you. Thank you, Team Depress System. Thank you.
All right, we've got the rhythm going already. So next up is Team Massimo. So we'll let the liaisons offer comments.
Well, this team did something that we weren't even sure we could get done ourselves. The real customers in Massimo are some algorithm engineers that are really trying to make sense of physiological factors, body factors, and translate that through materials. And the guys that write the algorithms to detect the physiological activities going on are not materials people. They really needed this model. So this has real practical applications for us. We had a tough time getting started because we didn't know how to advise the team and they didn't know what to do with what we were asking them to do. And we kind of stumbled our way through it. And over the course of 2 semesters, the product they came out with, the last presentation they gave to our real internal customers, our algorithm engineers were stunned at how accurate this model is. This is going to be a real valuable tool for us. And we have an engineer that's going to continue to take this model forward. And this will actually help us get medical devices to the market faster. So we really appreciate what the team did.
Thank you, Glenn. Sorry, do you want to say anything or?
It was my first experience working for the school after being graduated, and it was a great experience overall. And I'm really stunned with all the cool projects that I saw today. Good job, everyone.
Jack, would you like to give some perspective?
Thank you, Glenn and Sahar. Yeah, it was a real treat, Glenn pulling resources from the company to get us some technical advisors, Sahar and Justin Cable, who couldn't be here today. Having that technical background, like Glenn mentioned, of not knowing from the get-go where we wanted to go and turning to them, and when we weren't really sure what we were doing and them pointing us in the right direction, project would have failed without that. So thank you very much. From the students' perspective, I think it was a real learning experience to start thinking ahead. In our academic lives, we kind of just think about what's right in front of us, but thinking 5, 10, 15 weeks ahead and what we're going to have to provide for one another to make sure the project's on schedule. That really integrated us to what commercial products are really like. So thanks for that that lesson.
Thank you very much. Next up is Matrigenics. So Spencer, do you want to
Yeah.
talk about the fate of the liaisons?
Yes.
I know they're a small business. One thing
Yeah.
you have to do is try to raise money, so I think that's where they are.
Yeah. Unfortunately, liaisons couldn't make it, but we had Dr. Shreve Solomon, the CEO of Matrigenics, and Samir Shrine, who is also an advisor for them. Sharif was our biomedical advisor. He helped us a lot with the biomedical aspects of our product. And Samir really helped us with mechanical engineering. And they told us last week that they were really proud with what we've accomplished. We've gone from nothing to a physical device that you can see out there. So they're really proud of us. And as for me, really happy with my team. I could not have asked for a better team. I'm also it was a really great experience with the Mensch program. I could think of a lot of times where we were doing something Capstone and I thought, we just learned about that in Professor Don Rankin's class or Professor Barbara's class, and it was really applicable to what we were doing in an industry product. So thank you.
Thanks, Spencer.
Team Mitsubishi Electric. Like this offer, Eric.
Hi, everyone. In Mitsubishi Electric, we have a number of business units, and one of them is factory automation. And senior managers in that division told us that if drones can replace conveyor belts and floor-based robots, the business outcome would be huge. In this project, we wanted to show feasibility of that. And I would like to thank the team for the accomplishments, which will lay the foundation for a commercial product, perhaps in the next 2 years. And thank you, Farzad, as well, for your support.
My pleasure.
And yeah, we were happy to be a part of this initiative.
Thank you.
Thank you very much. Appreciate it. Thank you. Thank you for your support. So for our team's sake, I would say it's been a really great learning opportunity. We've taken this project basically from a very loose concept where we managed or were allowed to shape it a lot ourselves based on what we were interested in learning, but also what we were capable of doing. By having this great dialogue back and forth, we got a project that I think was really great for us. We explored a lot of new topics for us, such as computer vision, and also a lot of software side to this. And it's been a very great experience. I'm really thankful for the project and for how you've mentored us and helped us through the whole process.
Thank you. Thank you, team Mitsubishi Electric. Thank you. Thank you.
Okay, next team is Mivi. If you can please come up. And Myra, you're amazing.
Thank you. So I'm here to represent the company. Mivi is actually in Minnesota, but as part of my capstone, I was a UCI alumni, and I came into this company. We have a small company here at Cove. We call it Mivi Pacific. We have like 10 people here, but this is our second time that we're here with doing the UCI Capstone project. And I will say that this team really did the hardest job I have ever seen in teams. Like for them to build a code that will be used and will be part of the building blocks of our prototype, that is a huge, huge stepstone that you guys did. And none of them will be have been able to do with all your engineer skills that each of you had in different levels, different diversity as well. And engineer skills, your hard work, although we had obstacles, you never gave up, okay? I know you never gave up. And you had a team bond. You really had a team bond. And I think that engineer skills is not enough. They really had to be a team. They really had to work hard, and they had to have a great leadership like Erin. She was on top of everything all the time, and all of you were great. So thank you so much, UCI, for the Capstone project.
Thank you so much. Yeah, thank you, Myra. Myra was one of the best students in the MEng program. She was in the first cohort. Look at her now. All right. And Erin?
Yeah, I just want to start off by saying thank you so much, Myra. You know, it wouldn't have been possible had it not been for your continual support and guidance. You know, Myra spends nearly, 10-hour days in the lab. And so she was always available, always willing to help. And I also want to thank Vince, because without your feedback, you helped us to identify things that, we missed ourselves. And I think that really speaks to the power of collaboration. And just, I know that Dr. John Wainwright and Rithvij and Trent aren't here, but they did also help us tremendously. So I just would like to say thank you to them as well.
Thank you so much. Okay. Then finally, True Zero.
Hello, folks. My name is Greg Wallace. I represent True Zero. You know, I only got out of college a little less than 2 years ago. So the fact that I'm guiding students again is, I don't know, it's just funny to me. And since I was at school so recently, I remember how difficult thermal fluids and thermal fluid analysis is. So I want to say I'm very impressed with these guys' project. They got some excellent data and some excellent models for us. And so I want to thank them and thank the university for helping us make hydrogen fueling a reality.
Thank you so much, Greg. Thank you.
And then on behalf of the team, we just want to thank, of course, True Zero for sponsoring this project, as well as our faculty advisor, Professor Mintz. We really got to be on the forefront of a new technology, let alone gas stations. There's thousands of them in California, but True Zero is the leader, and there's only 41 hydrogen stations in California. So that just shows this new technology, and it's just getting started. I think it's definitely going to expand into, semi trucks, and we're really going to see an influx of hydrogen fueled vehicles. And it's going to be amazing for the sustainable. I think most of us here, we all care about the planet. So it's going to be awesome to be a part of that and just having experience as we move forward into our careers with hydrogen fueling. So thank you very much.
Once again, thanks to all the sponsors, the company liaisons, and all the students who worked hard for 2 quarters. Okay, the awards. There are 2 awards. One is the Dean's Award. One is the Executive Committee Winner Award. The criteria for these awards were innovative problem solving, quality of solution, and quality of presentation. Again, it was very difficult because all 7 teams really did great job. And the scores were close. Okay. The Dean's Award came from Dean Magnus, Dean of Samuel Lee School of Engineering. We had a runner-up team and the winner. The runner-up for the Dean's top choice is Team Advantage. Great job, Team Advantage. And the winner for the Dean's top choice, Metrogenics. So the team lead is going to receive this, and the rest of the team members, you are going to receive that during the group photo. So all of you are going to receive that. However, right now, only the team lead is going to receive it. Thank you and congratulations.
Your 15 seconds of fame. Okay, so then the second award is the Executive Committee Award. And so, like the Dean's Choice, this was very difficult. The committee put together their recommendations, and there was a runner-up for this award as well. The runner-up team is Matrogenics. But the winner of the Executive Committee Award is MIVI Neuroscience. Congratulations, please come up. Team MIVI. Okay, then to close things out, you know, it takes a village to run this program. Farzad and I have been up here talking with you, but really behind the scenes, all of these incredible people really deserve thanks. Jean McNeil, Emmanuel Giardo, Nikki Spratt, Debbie Lewis, Gisela Len, the TA Anita, thank you, and Alex Tran, who helped put on this great program here at the Cove. So give a big round of applause. All right, so that concludes the awards. Next are group photos. So our photographer, Vince, is going to guide us in that. We want to get photos of the students, sponsors and liaisons, and then all attendees. So that will be done right here. So all students first. Okay. So if you're a student, please come up. And you'll have to organize yourself maybe on 2 levels. I'm not sure.
So the picture you see here was your picture, your first picture as MEng student. And now you are going to have your last picture as MNG student. And starting from next week, you are going to be MNG alumni. Congratulations. So all the company liaisons, please join us. The company liaisons, please join us. Thank you. And you are going to take a group picture from everyone. All, please join us. Alex, would you like to join us? No? Nikki? Thank you.